So good afternoon. So it's my pleasure to be here. So in the following, I'm going to invite you to think of the nature of a weather. So here's my talk. The title of my talk is Weather Chaotic, Coexistence of Chaos and Order within a Generalized Lorenz Model. My name is Shen. I'm from San Diego State University. So I joined this school in 2014. Before that, I worked for NASA Goddard Space Flight Center on global model. So this work has been done with our colleagues, including Roger Piacchi. So I'm going to give you first present 30-day simulations to address our goal and approaches. Since it is a predictability study, so I'm going to review Lorenz models, and then I give summaries on the major features of a Lorenz butterfly. Then I'm going to propose, introduce a generalized Lorenz model with a focus on two kinds of attractor coexistence. Then based on what we discussed, we are going to propose a hypothetical mechanism for the probability of the case we discussed in the beginning. So after that, I will give a summaries. And here shows the 30-day simulations from our model. From day 22 to day 30, the model simulated a storm. Okay, so therefore we plot the locations as a function of time, as shown in the left-hand side. Okay, so and during the same period, there's a real Hurricane Helene from September 12th to 24th. We plot this base track. On the right-hand side, we plot the time evolutions of minimum serial pressure as function of time here. As you can tell, okay, during this period, the storm intensified. The model was able to simulate the rapid intensifications, but did not over-intensify the storm. Okay, based on these comparisons, and also as well as the analysis of environment force such as African slave wave, we suggest that the simulated storm resembled the real Hurricane Helene with respect to track and the locations. So we were lucky to publish the result smoothly 10 years ago, almost 10 years ago. And after that, we continue to think of how high-resolution model could have a scales. Specifically, we would like to understand, okay, if the model could have a scale at extended time scales. And gradually we realize we need to revisit, okay, examine the validity of the statement of whether it's chaotic. So therefore, during the past several years, we performed a comprehensive literature review and derive a generalized Lorenz model to understand butterfly effect, to reveal and detect the coexistence of chaotic and non-chaotic processes, to emphasize the dual nature of the chaos and order in weather, and to propose a hypothetical mechanisms. So next, we are going to discuss Lorenz model. We begin with definitions of butterfly effect. In our literature review, we point out there are at least two kinds of butterfly effects. The butterfly effect of the first kind is defined as a sensitive dependence on initial condition. And this feature has been widely studied in many fields. So this feature can be shown using the following figures. Here we plot, okay, compare two runs, control and parallel runs. And they use the same model and the same model configurations. The only difference is in the parallel run, we add very tiny perturbations that as indicated epsilon. Epsilon is equal to e to the -10th. Then we plot solutions as a function of time. Horizontal represent time. So initially, we only see one curve, which is the rate. So indicate two lines overlap. So that indicate, okay, continuous dependence on initial conditions. And then later, we do see two different lines. And these differences is associated with very tiny perturbations. So therefore, this stage is called sensitive dependence on initial conditions. We refer this as B1 butterfly effect of the first kind. And that is also known as chaos. And in 1972, Lorenz applied this feature to study the possibility for a butterfly to create a tornado. So in our literature review, we believe, okay, there's no theoretical foundations to support this idea. And therefore, we refer this as a B2 butterfly effect of the second kind. So within this study, we focus on B1. So here shows the Lorenz model. Later, we are going to compare to the generalized Lorenz model. Here shows three. First of all, the ODE consists of X, Y, Z. And X, Y, Z represent the amplitude of a frame mode for the stream function and the temperature. We can use X, Y, Z to define a phase space. So therefore, the dimensions of a phase space is equal to number of variables. In this case, so therefore, in this case, that is a three-dimensional. So therefore, we also refer the Lorenz model as a three-dimensional Lorenz model. A solution in the phase space is called trajectory or orbit. Here, okay, we have a two nonlinear terms. Okay. And our analysis suggests that these two nonlinear terms form a nonlinear feedback loop. Later, when we discuss generalized Lorenz model, that is derived based on the extensions of a nonlinear feedback loop. In addition to the time-dependent variables x, y, z, on the right-hand side, we have a time-independent parameter, including sigma, r, and b. In this study, we've simply focused on the impact of different r. R represent the Rayleigh numbers. That is a measure of a temperature differences between bottom and top layers. Okay, so that is a Lorenz model. So within the 3DLM Lorenz 63 model, the chaotic solutions has been a focus. Okay? However, here we want to emphasize that chaotic solutions only appear within a finite ranges of R. Let RC represent the critical values for onset of a chaos, which is equal to 2474. So if R is less than RC, the solution approaches to constant when time proceeds, and this indicates a steady state. And when R is greater than RC, we do see, okay, two control round and the pair round produce a very different result, and these are chaotic solutions. Interestingly, when R is sufficiently large, the model produces as a later signature, which is known as a limit cycle solution. And this solution can be better, this is solutions into this space. So the limit cycle solutions can be better discussed using the following figures. Here we plot the 200 orbits in color, and that using different initial conditions. And during the last one-time unit, we also plot this 200 orbit in black. So therefore, we can see how 200 orbits converge into a single orbit in black. And this indicates the isolated features of limit cycle solutions, namely nearby trajectories spiral into the single orbit. Limit cycle solutions are determined solely by the distance. However, if we plot the two of the orbits as a function of time here, we do see two solutions produce the same amplitude. However, the phases are different. So the dependence of the phases on initial condition lead to the oscillatory errors. So we are going to use this feature to analyze our 30-day simulations later. So within the 3DLM, okay, so we have three types of solutions. For the first and the third type of solutions have no long-term memory regarding the initial conditions. For chaotic solutions, any tiny perturbation can create huge differences in the time evolutions of a solution. So some people use this to kind of using the Fourier analogy to illustrate this. Any individual can create huge impact in all kinds of environments. So we can ask if such feature is realistic. So we are going to address this using a generalized Lorenz model. Before that, I'm going to show you, okay, the high temporal resolutions from our global model. And this animation was done 15 years ago. So this shows how initial shock dissipated by the system. So I hope you agree with me that, okay, the initial shock does not create a huge impact on the subsequent simulations. So Lorenz model has been used to illustrate the chaotic features. However, Lorenz model only has three modes, so that has a limited scale interactions. So therefore, it's not good to address the multi-scale interaction between a butterfly and a tornado. And Lorenz has other models such as the 69 model and the 96 model. And this model has their own limits as well. For example, 69 model is a linear system. And the 96 is not derived from PDE. And also, Lorenz has 84 model. 84 model has their own limits as well. So therefore, we have to know the limits of this model and interpret results with quotients. Okay. So next, we are going to summarize the major feature for butterfly patterns. Lorenz pattern. So there's no universal definitions for chaos. However, it's accepted that the B1 butterfly effect of the first kind is a major feature for chaotic system. And B1 leads to the following or comparable to the following two features. The first one is long-time average divergence of a nearby trajectory. The second one is solutions boundedness. And these two lead to recurrency folding. And the statement, orbits initially diverge and curve back. Okay? And because of these features, so error should be finite, okay, limited by the size of butterfly wings. And at a kind of a chaotic region, we expect error saturations. And the last one is the kind of a foundation for the ensemble remodel approach. So based on what we discussed, we can use the following, folklore to test our knowledges. Okay? This has been used as a knowledge of a butterfly effect. It does folklore simply state the loss of a nail leads to loss of shoes, hose, rider, bridle, and eventual kittens. So based on what we discussed, we can say this is not a very precise analysis of a butterfly because it simply describes the phenomena of instability with unbounded solutions. In our view, we believe that this verse does not describe local time-varying divergence and the convergence of nearby trajectory, nor indicate recurrency. So with that being said, we are going to introduce our generalized Lorenz model. So the generalized Lorenz model has been derived based on the extensions of a nonlinear feedback loop. So it is a kind of, it allows any odd number mode. And it is a conservative systems in the exceptionless limit. So next, we are going to focus on the following features, including slow and fast variables, aggregated negative feedback, and the two kinds of attractor coexistence. So here, again, this is the original Lorenz 63 model. XYZ now are referred to primary scale modes. Through kind of a simplification, say that you ignore the dissipation term and perform nonlinear linearizations, we can show that the backbone of this system is analogous to a system with one mass and one spring. Then we extend the nonlinear term by adding this that is based on the analysis of a Jacobian. So we can, each time we add additional pair of small scale mode, Yj and Zj, and we can repeat it to do that. Okay? Using a similar idea approach, you can show that the subsystem, a simplified subsystem, is equivalent to, is analogous to a system with one mass and one spring that has a different spring constant. Namely, the additional pair of small scale mode introduce a different frequency. So we can repeatedly do that. So therefore, it allows, J is a very huge number. So if we simply compare equation 2 and 4, we realize, Yj is a fast variables, and Y is a slow variables, And the so-called aggregated negative feedback has been discussed in mathematical derivations in the paper. Here we simply show the results. Here, this first column indicates the number of modes. The second column indicates, again, RC, represent the critical values of R for onset of chaos. So here we can simply consider GLM with the 3 modes, 5, 7, and 9 modes. Okay? Comparison among these 4 models indicate that a higher dimensional Lorenz model requires a larger R for onset of a chaos. So therefore, this indicates that aggregated negative feedback means that each time we add additional pair of small scale mode, you provide a negative feedback to the system. More important, all kind of negative feedback can be aggregated to provide a stronger dissipation. So therefore, high dimensional Lorenz model becomes more stable. Okay, so as mentioned earlier, additional pair of small scale mode can introduce a different frequency. And we can, based on the following mathematical derivation, we can learn a little bit more. For example, if we consider a system with a prescribed forcing on the right-hand side, and we know that this kind of autonomous systems can be written in this way. Okay, means the external forcing can be written in terms of a pair of first order ODE. So therefore, we can say that high dimensional autonomous systems can be viewed as low dimensional systems coupled with forcing terms. So next, we are going to discuss the first kind of attractor coexistence. Now we simply use the GLM with 9 modes. That is referred to as a 9DLM. Here we present 3 cases with 3 different initial conditions. For the first two, we see the solutions eventually approach a constant. So these two are steady state. In the third case, we do see control run and the pair run produce very different results. And this is the chaotic solutions. Again, the solutions in 2D space is shown in the bottom. So this is the first kind of attractor coexistence. So the next one we present, the second kind of attractor coexistence. Here we show 2048 orbits. And at a given time, we only plot orbits for the last 1/4 units. So therefore, you will see some of orbits eventually converge to an orbit. That is limit cycle solutions. Again, limit cycle solutions is defined as isolated closed orbits. And you will see for the rest of the orbits, they kind of spiral into one of the point attractors. Here, at this time, you can see clearly, this is the limit cycle solutions with the largest, spatial scales. So because of the attractor coexistence, the 9DLM does reveal the following features. The first one is the final state sensitivity to initial conditions. So in this case, any initial conditions may be important or unimportant, depends on which kind of attraction, based on attractions. However, compared to the 3DLM, any tiny variations is important. So therefore, based on our analysis, we suggest that the coexistence is more realistic features. So based on what we discussed, we are going to analyze the results from the 30-day simulation again. Here, this time we plot the correlation coefficient in the vertical axis as function of time. And as you can tell, during the 30-day period, the correlation coefficients are about 0.6, which indicate a good predictions. However, on the other hand, we also notice that the correlation coefficient oscillates with time. And based on what we discussed for the oscillatory features for limit cycle solution, I hope you agree with me that these features are not unrealistic. So this slide provides a little bit more comparisons. Limit cycle solution appear when strong heating is balanced with nonlinearity. And during the summertime, the strong solar radiation are over African continent. So if the stronger surface heating can be balanced with the non-reality, we may expect oscillatory signature. And that is consistent with the view that considered with the fact that each year there are 27 arbitrary state waves. Okay, so therefore, here we do see the oscillatory correlation coefficient may be analogous to the oscillator errors in limit cycle solutions. So based on what we discussed, so therefore the realistic simulations of Hurricane Helene from day 22 to day 30 becomes possible as a result of a realistic simulations of periodicity for arbitrary state wave, and also downscaling of the fourth arbitrary state wave. And the fundamental assumptions for the previous mechanisms depends on existence of oscillatory components. And this slide provides additional support for those kind of features, including, actually in the book published by Lorenz in 1993, he also suggests 3 types of solutions, including vacillation. And the vacillation can be viewed as limit cycle solutions. And in 2002, Gill and his colleagues suggest that limit cycle models can be used to illustrate the 40-day period of intra-season oscillations. And based on what we discussed, I'm going to give a summary. And in this talk, we pointed out there are 2 kinds of butterfly effects. We focus on the first one, B1. And within a generalized Lorenz model, we focus on 2 kinds of attractor coexistence. We also suggest that a high-dimensional Lorenz model can be viewed as a low-dimensional Lorenz model with forcing. We want to emphasize chaotic solutions only appear within a finite range of heating parameters. Chaotic and non-chaotic solutions may coexist, display 2 kinds of data dependency. So therefore, B1 does not always appear. Before Lorenz, everything centered around periodic solutions. After Lorenz's 63 and 72 study, many people focus on the existence of non-periodic solutions. So we propose that the entirety of the way the persists dual natures of chaos and order. So this type of duality should be taken into consideration to revisit predictability problem. So for future work, we would like to perform analysis to looking for oscillatory signature. Especially we have a tool that can help us to remove the local mean, and that we call PEMD. And we also would like to improve the model simulations for the nonlinear oscillatory signals. We believe that it is important to reduce numerical dissipation to avoid computational chaos. And this is a takeaway message. In addition to duality, we want to say that we agree with Kawa. There's no reason that the limits of predictability is too weak. In some cases, actually, we obtain realistic simulations beyond 2 weeks already. And I'd like to thank the following colleagues for their support and helpful discussions. And thank you. This concludes my talk. I would like to take questions.
Any questions, comments? Yeah, Stefan?
Yeah, we have discussed it for a long time, yeah.
So my first question is, so you were asking yourself, is weather chaotic? So what is your conclusion?
So weather is chaotic, the statement is not very precise because weather should have non-chaotic components.
Well, okay. But
so if people agree, weather is chaotic also means it also includes non-chaotic component, that's good. Otherwise, I just want to emphasize that weather should have include non-chaotic components.
I have another point. So you mentioned that you can have coexistence of periodic orbits and chaotic solutions. Of course, you can also have unstable periodic orbits that are below your, let's say, the backbone of your chaotic attractor. So the oscillating behavior you can see in your dynamics can also be related to simply to that, because you are passing close to an unstable periodic orbit. So
it's not good.
It should not be stable.
The point is that if the weather consists of both chaotic and non-chaotic, it means the key is that the butterfly effect of the first kind does not always appear. That's the key issues. So therefore, for some kind of noise like here, we don't have to worry about too much. That's the key. And in terms of numerical weather predictions, we should not have too many concerns on all kind of noises. That's the main issues. Yeah.
Okay. In the interests of coffee.
In the interest of coffee.
Okay.
Okay, in that case, I'll just make it a statement instead of a question. No, I won't. So Ed Lorenz also used to say that it just wasn't a question to ask whether or not weather was chaotic. The question we should ask is whether or not our best models of weather are chaotic or not. And then we might say that means weather is chaotic, but everything might change tomorrow. I'm just sort of curious in this dual nature and these. I realize you have a different quote. Okay, I'm just curious how you. And so Mach used to say the same thing. We shouldn't argue about stochastic or deterministic because we can never tell. So we should go ahead and
that's another
study.
issue. So the first,
do you think that holds?
First, I think it is important for us to distinguish so-called chaos or so-called computational chaos. So if there's a chaos in the model, it doesn't mean the nature of weather is chaotic. That's my point. And also in many cases, for example, even for Lorenz in 1989, he studied so-called computational chaos using limit cycle solution, limit cycle models. So it is possible, So even the model has a limit cycle solution. However, because of numerical dissipations, the numerical solution becomes chaotic. So therefore, to me, if the weather persists of dual natures, so from practical perspective, we will add a kind of another layer because right now we have a final state sensitivity. However, as long as we can detect oscillatory or non-chaotic component, we should expect higher predictability for those processes. Yeah.
That sounds like a very good coffee break conversation. Thank you again very much.
Thank you.